So in this module, I just wanted to look at another very quick example problem using some slides that were already pre-made by the text, just to make sure that everyone understood a lot of the concepts that we covered in the last few modules. So we have a crane. We've actually already looked at this free body diagram. If you remember, it is supporting both its own weight, which we can compute given its actual mass by multiplying by the acceleration due to gravity. And we know where to apply that weight in terms of the free body diagram because we're also given the center of gravity of the crane. So the crane is supporting its own weight. It's also supporting the weight of this mass, which is attached via the cable to the pulley. And in order to kind of counterbalance those two downward forces that are exerted at different horizontal distances from the wall support, we have the two ends of the crane constrained by both a pin support along with a roller support. And if you look back to the actual table that we discussed a couple times in this actual lecture, you will see that a pin support, right? If you think about something being pinned in, it can't actually oppose any rotation about that point. It can stop things from moving left or right. It can kind of pull it back in. It can stop things from moving up and down, but it can't actually oppose rotation. So the reaction of the pin connection is going to be an unknown horizontal and vertical force versus the rocker connection. It's not going to be able to oppose motion parallel to the wall, but if it gets pushed back into the wall, it can allow a force to push back out and exert a force perpendicular to the actual rocker. So that's what's really going on here if you think about it. The only thing that can oppose the actual downward force of the weight of the crane and this mass is the vertical component of the reaction at y. However, if you think about it, what is going to happen is these are going to, if we talk about the tendency of these two forces to exert rotation about point A, the reaction at A can't counterbalance its tendency to swing in the clockwise direction. So that's why you basically need B. So B is basically going to be pushing back out in order to stop it from swinging this way. And if we have something pushing back out, we need something pulling it back in. So that's, as we'll see when we get to the solution, why we need that support structure. So obviously the first thing we have to do is draw the free body diagram. We're interested in analyzing the equilibrium of the crane. So we're going to separate it from its support structures. We're going to show the effect of both the loading on the actual body, which is going to be the weight of that applied mass. We compute this by taking 2,400 kilograms and multiplying by the acceleration due to gravity. That's how we're going about and getting this 23.5 kilonewtons. In addition, we were given the mass of the crane, 1,000. If we multiply by acceleration due to gravity, 9.81, that's going to give us a weight of 9.81 kilonewtons. We're applying it at the center of gravity, which we were told to be G. We need to be told that. We don't know how to compute it yet. And in addition, we're replacing the effect of disconnecting the crane from the two support structures at A and B by unknown reactions in the horizontal and vertical direction at A and an unknown reaction in the horizontal direction at B. Now, automatically, you're going to notice when we sum all forces in the x direction on that body, AX or B is going to turn out to be negative. And that's okay. We always want to have a standard convention by which we show our unknown reaction forces. And if it turns out that we misassumed the sense of those reactions, that's okay. The math will just allow one of them to work out to be negative. So let's actually go about solving for our three unknowns in this case. We do have a statically determinate situation because we're going to be able to write our sum of resultant force equal to 0 in two dimensions. That will give us two equations, and we'll be able to write our moment equation as well. So we'll have three equations to solve for these three unknowns. So the first thing that the book chooses to do, and this is a very common approach, is to sum all moments about point A. Now, why would you do that? Well, you have three unknowns, but two of them have line of actions that pass through point A. And whenever you have a force that has a line of action through the point, hopefully you remember that the moment of that force about that point is 0. It doesn't contribute. So if we sum all of the moments about point A, the only unknown that will contribute to that equation is unknown B. So that will allow us to solve for B directly. And that's why the text did that. So let's talk about the moments that these two forces exert about point A. So if you imagine having this crane and you have it pinned at A, and you actually pull it in the downward direction, whether you pull it out 2 meters or out 6 meters, in both cases, it's going to tend to rotate it in the clockwise direction. So that's why the moment associated with both the weight of the crane along with the applied weight is negative because you're having a clockwise rotation. However, if you think about the rotation that this force applied at B is going to exert, clearly if you have this thing pinned and you push it out, it's going to rotate it in the counterclockwise direction. So it gets positive. And that's showing you exactly what we said. If there were no other support structures other than A, this thing would tend to rotate in the clockwise direction. And B is counterbalancing that rotation by pushing back out. So in terms of the perpendicular distances that we need, we're computing a moment about point A. If we extend the line of action of the horizontal force B and we draw a perpendicular line from A to B, that's just going to be 1.5 meters. So that's where that number is coming from. For the two vertical forces, if we look at their vertical lines of action and we draw perpendicular distances from point A, that is just going to be nothing more than the specified distances that were given at the bottom. The perpendicular distance to the 9.81 kilonewton weight is 2 meters, and the perpendicular distance out to the applied load of 23.5 kilonewtons is 6 meters. So that's where the actual 2 and the 6 are coming in. So hopefully everyone sees that. And then we can solve this for B, and we can determine that the magnitude of that unknown reaction is 107.1 kilonewtons. So that's just what we said at the beginning. B is having to push this crane back out to stop it from rotating in the clockwise direction. Well, if B is pushing it back out, AX is going to have to be pulling it back in. So if we sum all forces in the X direction, notice that by the convention we assumed, it's AX plus B. But if B is positive, and of course AX plus B is equal to 0, since it's not moving left or right, if we solve that for AX, what we're going to find is that AX has to simply have the opposite value of B, so it turns out to be minus 107.1 kilonewtons. That's just saying that the direction we assumed for AX was incorrect because AX has to pull the crane back in. Finally, in order to solve for the actual unknown vertical reaction at AY, all that we have to do is sum all forces in the Y direction. And basically what that's going to tell us is we have a positive AY minus 9.81 kilonewtons minus 23.5 kilonewtons, all equal to 0. We can solve that for AY, and we basically see that AY has to be the sum of the magnitude of the weight of the load and the weight of the crane. So it is basically holding that thing up as its weight is pulling it down along with the weight of the load. The one thing that the book is emphasizing in this next point is that once you have the value of those unknown 3 reactions, you can actually go about and you can sum all moments about any point on this crane, and you better find that they turn out to be 0. Because remember, the first thing we talked about in this chapter is that for rigid body equilibrium, the sum of all moments about any point has to be 0. So one way that we could check easily is to look at the sum of all moments about point B. Now, why would we choose to compute the sum of all moments about point B as opposed to some other point on this structure? Well, remember, when you're computing moments, the first thing you have to do is make sure that you have the dimensional information you need in order to compute the perpendicular distances. So that's one reason that you're doing it. But another reason it's convenient to compute all moments about point B is that both the reaction at B, that 107.1 kilonewton force, along with the Y component of the reaction at A, the 33.3 kilonewton force, they don't contribute a moment about point B because their lines of action pass through point B. So when I'm considering the moments about point B, all that I'm doing is describing how the weight of the crane, along with the weight of the load, which both induce clockwise rotations, are counterbalanced by the X component of the reaction at A to actually pull back and induce a counterclockwise rotation. So that's where these signs are coming from. The minuses are simply indicating that these downward forces about point B are going to induce a clockwise rotation, versus the horizontal force applied at point A is going to induce a counterclockwise rotation. So it gets a plus. In terms of perpendicular distances, again, if we're computing about point B, this horizontal force is going to have a perpendicular distance that's simply equal to this 1.5 meter specification that we were given. And these two forces, they have lines of action which are vertical. If we measure the perpendicular distance from point A, those are just going to be the two specified distances that we have, 2 meters and 2 plus 4 meters, which is 6 meters, which is where these two values are coming from. Again, both negative because they're both inducing clockwise rotations, positive for the actual reaction of the X component A because it's inducing a counterclockwise rotation. So I hope that that was a good start for this chapter, and we will get the homework posted, and good luck on that.